everybody, and welcome to part 3 of Related Rates. So in our last recording, we talked a little bit about this camera and the rocket being launched, and the camera is actually looking up and following the rocket wherever it goes. And in part A, we talked about how the vertical distance and the distance between the camera and the rocket, we wanted to talk about how they were changing. And they were size of a right triangle. And so we used a Pythagorean theorem to relate those sides together. In part B, which is what we're going to tackle now, it talks about how fast is the camera's angle of elevation changing. And so the first thing we need to do is we need to go to our picture and find the angle of elevation. And that is always the angle from the line of sight up to the object. And when you deal with angles, you normally call the angle theta. We either use theta, alpha, or beta when we're talking about angles. And so I'm going to use theta. That's the most commonly used. So we need to find a relationship between this angle and other things that we either know or want to find. And so all of the information given in the original problem is still true. So all of this is still true. And that actually needs to be 3,000 right there. Let me change that. Got to erase. That needs to be 3,000. There we go. And so I need to find a relationship between this angle and some sides of a triangle. And if this is a right triangle, then I want to use a relationship that is normally used with angles and right triangles, which is the trig functions. So which trig function can I use? Well, I can use any of them, but I want to use the smartest one. And we know that this distance right here is 3,000. And it's always 3,000. I cannot use the 4,000 because it is instantaneous information. I can only use that piece after the implicit differentiation, but I can use the 3,000 in the setup because it never changes. So I know dy dt, and I know something about x. So what relationship relates y and x to the angle theta? And that's going to be tangent. So I'm going to use the relationship of tangent to relate the things that I want to find, because it says how fast is the camera's angle of elevation changing. So in this case, I really want d theta dt when all of that is happening, right? Because all of that does not change. So I need a relationship with a theta in it. So tangent theta equals y over, and normally I'd have to put x because x changes, but because in our problem that's a set 3,000, that's going to make our problem easier. Again, we could have used any other ones, but it would have been a harder process. So let's implicitly differentiate. So the derivative of the derivative of tangent is secant squared theta. And don't forget, we've got to do that chain d theta dt because everything's changing with respect to time. And if you think about that as 1 over 3,000, so this is really 1 over 3,000 y. Really, that's kind of how you can think about that. Then the derivative of 1 over 3,000 y is 1 over 3,000 dy dt, because that's that chain rule. Everything is changing with respect to time. And so now this is the part where we plug everything in we know, and hopefully the thing that we're trying to find, which is d theta dt, is the only thing left. Well, I know dy dt. I can put that in for 800, but I don't know secant squared of theta. You know what I'm going to do? First, I'm going to solve this. It might make it a little easier. You know, remember that secant squared theta is really 1, sorry about that, didn't mean to do that, is 1 over cosine squared theta. And so really, this is like 1 over cosine squared theta. So to get rid of it, I would really multiply both sides by cosine squared theta. So let me do that. So d theta dt is equal to 1 over 3,000. I'm going to go ahead and put my dy dt in there of 800. And then the only thing I don't know is cosine. I'm going to write it like this because I want to make sure that I understand. I'm trying to find cosine of theta. When I do, I need to square it. So remember the triangle that we used before that's called the instantaneous triangle? That's that triangle right there. And after you implicitly differentiate, you can use that triangle to find different sides, or in this case, a trigonometric relationship. So d theta dt is equal to, I need cosine of theta squared. So I'm going to go ahead and knock out some zeros here. So I get, let's see, 2, so that's going to be 4 over 15 is what I get there. And I need to find cosine of theta. And when I do, I'm going to square it. So cosine of theta, this is theta, would be adjacent over hypotenuse. So that's going to be 3/5 because all those zeros would cancel, and I need to square that. And so I end up with 4/15 times 9/25. And that ends, I'm going to cross cancel here a little bit. Let me grab this, push it up a little bit so you can see my work. So I'm going to end up with 4 and 3, that's going to be 3, and that's going to be 5. And so that ends up being 12 over, let's see, 4 of those would be 100, so 125, right? And I need to put a measurement on this. Remember, this is a rate. This is d theta dt. And so how does theta change? Well, theta changes in the measurement of theta, which is radians, and the time is in seconds, so it's radians per second. Okay? So that is how fast the angle is changing that the camera forms with the line of sight and the line of sight of the rocket at the point where y is 4,000 feet off the ground. It's 12 over 125 radians per second. Okay, that concludes part 3, and in part 4 we're going to do some different kinds of problems, so please come back for that.